Okay, so welcome back to Parameterized Algorithms in 2021. Today we have the last lecture on algorithmic part of the theory. Namely, I would like to tell you about the technique of representative sets, which is another algorithmic technique that emerged somehow somewhat around 2012, 2013. And it is kind of a technique that applies to similar problems as, say, color coding or algebraic techniques that we have seen during the previous lecture, but it is quite different in nature, and I think it's nice combinatorially, so we would like to cover it as well. So we will present the technique on a problem. It will apply to different problems, but let's fix a problem of interest. As usual in this kind of things, we will be working with the directed k-path problem. It is a problem that to which all of those techniques can be applied. Just to recall, we have a directed graph D, and we ask whether D has a simple path on k vertices, where simple means that I cannot repeat a vertex along the path. So for instance, if you look at this directed graph here, I can start, for instance, in this vertex and then go like that along the edges respecting the direction. And in this way, I created a simple path on 10 vertices, I think. So yes. So what we have seen before, we made algorithms using two different techniques for this problem. The first one was this color coding technique, where you randomly sampled coloring of the vertex set with colors, and you were looking for a colorful path. And there we designed an algorithm with running time 2e power k times polynomial, an FPT algorithm. And this was a priori it was a randomized algorithm, because what we did is we sampled the coloring and then looked for a path, and the path was there with high probability. But we eventually managed to get it into the deterministic algorithm using this deterministic algorithm using this splitter or universal hash functions. There was something that we needed to pay for this the randomization. Probably we added here plus small o of k for the randomization. Then later on we designed this algebraic technique, so coding problems through polynomials and using the polynomial identity testing using Schwarzschild lemma. And using this technique, we managed to get a 2 power k times poly an algorithm for directed k-path, and this was inherently randomized. So it is currently not known how to de-randomize algorithm using Schwarzschild lemma. So what I will try to tell you today about is an algorithm with running time 4 power k plus small o of k using representative sets. And the point here is that this is actually deterministic. So the representative sets is a technique that applies to the same kind of problems, but it is an inherently deterministic technique. It yields slightly worse running times, but has the better properties of the algorithm, and it is significantly different. So let's try to get some intuition about how the technique will actually work. So we are looking for a k-path. And the k-path, as usual, it starts with a path of length 1, then it is extended to path of length 2, to path of length 3, and so on and so on. So you can think of construction of a k-path as prolonging a longer and longer path, subject to the condition that at every point I cannot reuse previous vertices. So in particular, if I fix some p, yes, which is an integer between 0 and k, then I can think about partial solutions of length p, which are just prefixes of our path of length p. So for instance, if I'm looking at a partial solution between u and v, these are two vertices, I'm thinking about a partial solution, a partial path that starts at u and at v. Yeah. So for instance, a uv path on p vertices could look like that. Yeah. Go through p vertices in the in the middle, and then later on, maybe we will extend it to a path on k vertices. So let's look at the family of all possible such partial solutions. So let this P UV with superscript P be all partial P partial solutions between U and V. So with start U and end V. So this is a family of paths, and a priori there can be very many of them, right? In the worst case, I can have as many as n to the p such paths, because maybe this is a path on p vertices, maybe here is another path on p vertices from u to v, maybe here is yet another path, yeah, that goes somehow, and all these paths can somehow behave differently, and the way they behave between u and v affects the possible extensions, right? Because if I want to extend, for instance, this path looking using a path looking like that, for instance, then this extension, this red extension, it fits the orange partial solution because they are disjoint. Yes. However, it does not somehow fit the pink and the blue solution because they are not disjoint. Yeah. So the red extension only fits to one possible partial solution from the one that I drew here. Yeah. So there is a notion of fitting between the partial solutions and possible extensions of them in the future. So the key intuitive observation behind the representative sets is that for the set of remaining Q vertices, we only care that they are disjoint with some partial solutions. Yeah, that given a partial solution on one hand and a possible extension, we have this notion of fitting. And somehow at the beginning, we have this huge family of size n to the p of all possible partial solutions. But maybe if we care only about disjointness of whatever happens in the future, maybe we can restrict attention to some smaller subfamily of these solutions. A subfamily maybe of some FPT size instead of n power p. And this is vague at this moment. So now let's make them the main definition of this lecture that formalizes this idea of restricting to a smaller family of witnesses, and this smaller family is called the representative set. Hence the name of the technique. So imagine I've got some universe U. Yes, in our case, this universe will be the vertex of the graph, and I have some family F of subsets of this universe, subsets of size P. So F consists of P subsets of the universe, subsets consisting of P vertices. So imagine you should think of P as partial solutions to your problem. And then I would like to restrict my attention, given this large family F, I would like to restrict my attention to a subfamily F hat. This is a representative set that Q represents F. And what does it mean that this F hat Q represents F? It means the following. Whatever happens in the future, so for every possible subset of Q vertices that will come, if there is a set P in F that fits to Q in the sense that they are disjoint, then actually I can also find a witness in my representative family. So a set P hat that is also disjoint with Q. So to look at it on the picture, here are some partial solutions. Yes. And here is some possible extension. Yes. And if we find something in my full family F that fits to this extension in the sense that it is disjoint, then we can also find something that is disjoint with it in my representative subfamily F hat. Yeah, so F hat is like a robust set of witnesses. Whatever happens in the future and extends some partial solution, it also extends some of those interesting partial solutions. So relevant partial solutions. So is this definition clear? Maybe you can put some +1s on the chat if you are happy with this definition. I do not see too many +1s. Are there any doubts about what happens here? Any questions? Should I repeat something? Okay. Maybe for those of you who feel a little bit lost at this point, maybe it will become clear later on how this exactly works when we see it on example, how this applies to the problems. But the intuition is that a representative family is a subfamily consisting of somehow relevant witnesses, in the sense that whatever a future brings us, yes, if this future is compatible with one of the partial solutions, it is also compatible with one of the partial solutions within my representative family. And the key point is that actually there exist representative sets of very small size. So imagine that we've got a family F consisting of P subsets of some universe U. Then I claim that I can always find a representative subfamily that Q represents F. Yes, here P and Q are fixed parameters. Yes, and it is of very small size. It is of size at most P plus Q choose P. So note that this size is independent of the size of the universe in particular, right? So we can find a really, really small subset of relevant witnesses that fits every possible future, provided that something in the future, that something in my family fits this future. Okay, so this is a combinatorial lemma. Let's prove it. So the proof will be sort of greedy, in the sense that we will make smaller and smaller representative family. So clearly the whole family Q represents itself, right? You just look at this definition and well, the same set P satisfies the right-hand side of the implication. Yeah, so we can start with the family F and then iteratively remove elements from F until we get some representative family F hat that is minimal subject to representing. Yeah, so I take a Q, a subfamily F hat of family F that Q represents F and is minimal with respect to this condition. And I claim that if inclusion-wise minimal. So I can compute it by just taking sets, and as long as I can remove something, I remove something. And I will prove that if I take a minimal one, inclusion-wise minimal, it is already small. Any inclusion-wise minimal subfamily Q representing F is actually of size at most P plus Q choose P. Okay, so let's think about what this minimality actually means. What does it mean that the family is minimal? It means that if I take anybody from my minimal from my minimal family F hat, yes, I cannot remove it while preserving representativity. So this means why I cannot remove it, because there is some future B, yes, there is some Q subset B, a set consisting of Q vertices, for which A is the only possible witness, in the sense that A and B are disjoint, so A and B fit to each other. However, if I removed A from my family, there would be no witness anymore. So for every A prime different from A, yes, I have that A prime and B are not disjoint. Yeah. So then the removal of A would actually mean that this future does not does not satisfy the condition of representativity. So all in all, if I look at the guys from F here, say A1 up to AL, where L is the size of F hat, yes, then for every AI, I can find the corresponding BI where I have the following situation. So AI and BI, they are disjoint. So they are disjoint in pairs. So this means disjointness. However, whenever I'm looking at AI and BJ from a different pair, then actually in here, they do intersect. So sort of interaction between the AIs and BIs is like a co-matching, a complement of a matching. Yes, that in pairs they are disjoint, but not in pairs they actually do intersect. Yeah? So this is a pretty restricted combinatorial structure. And we will prove, and this is something that is called the Bollobas Lemma, that if we have exactly this structure, then this structure cannot be too large. Namely, if I've got some subsets of a universe of size P and another sequence of subsets of universe of size Q, with exactly this property that in pairs they are disjoint, but across the pairs they do intersect, then this structure cannot be too large. It is of size at most P plus Q choose P. Yeah, and this will end the proof, right? Because we took the minimal one, a minimal Q representing family, Q representative family. We have obtained this structure from it, and if this structure cannot be too large, then this means that the family itself could not be too large. Okay, so we are left with proving this Bollobas Lemma, and the proof of Bollobas Lemma actually it fits here. So it is really simple and maybe not simple, but really quick. But it is a very nice application of the probabilistic method in combinatorics. So the proof goes like that. So I've got this this universe U. So let me pick a random ordering of this universe. So here, let sigma be a random ordering of my universe. I just sample uniform at random some order of elements. Yeah. So if I look at some particular AI and particular BI, then it may happen that in this ordering, the whole of AI is before the whole of BI. Yeah, I can put a line between them so that all the AI is before the line and all the BI is after the line. Yeah? So let this be event EI. So this is an event in my probabilistic space. Yeah? So what is the probability that this happens? Well, there are P plus Q elements of AI union BI. Yes, AI and BI are disjoint, right? So this is why this can happen. Yes, that all of AI can be before all of BI. There are P plus Q elements of AI union BI, and these particular P elements of AI must be the first P ones, right? So there are P plus Q choose P ways of choosing the first P ones, the first P elements of all of those P plus Q elements. So the probability that the P first ones are exactly the elements of AI is 1 over P plus Q choose P. So this is observation number 1. And the second observation, which is crucial in this proof, is that actually these events are pairwise disjoint. Why so? Well, imagine that I have a situation where AI is entirely before BI, but also some AJ is entirely before BJ in my ordering. However, I know that both AI and AJ and BI they intersect, and I know that AI and BJ intersect. But one of those lines, either the green line is to the left of the red line, or vice versa. And in both cases, you see that this AI, because it is before the green line, which is before the red line, which is before all of BJ, yes, this implies that AI and BJ must be entirely disjoint. Yes, and of course, if it was the other way around, if the green line was to the right of the red line, then AJ and BI would be disjoint, which is a contradiction with this condition. Right, so we have the second observation that the events EI are pairwise disjoint. So what do we have? We have L events, yes, that are pairwise disjoint, And each of them has this probability. So I can write it like that. That probability that any of those events happens, yeah, clearly it is upper bounded by 1 as any probability. Yeah. Then this is equal to the sum of probabilities because the events are pairwise disjoint. Yes, and this is actually equal to L, the number of events, times the probability of each of them. So now from this, you see that L is at most P plus Q choose P. You simply cannot pack more than P plus Q choose P disjoint events into the probabilistic space when each of them has probability 1 over P plus Q choose P. Good. So this was the proof of Bollobas Lemma, which also proves our statement that I can always find a Q representative family of size P plus Q choose P. Are there any questions to this proof? Or maybe you can put a +1 in the chat if you are happy with this proof.
Can you repeat the proof of observation 2?
The proof of observation 2. Good. So let me remove the my picture and let me draw it again. So I have these two pairs of sets, AI, BI, and the second pair is AJ, BJ. And I know that AI and BI are disjoint, AJ and BJ are disjoint, but AI and BJ are not disjoint, and BI and AJ are not disjoint. So if I now imagine that both EI and EJ happened, so AI is entirely to the left of BI, and AJ somewhere is entirely to the left of BJ. So this means that I can put a line, yes, here, a green line, such that the AI is entirely to the left of this line, and BI is entirely to the right of this line. And similarly, I can put a line between AJ and BJ. So suppose without loss of generality that the green line is to the left of the red line. But then AI is entirely to the left of the green line, which is entirely to the left of the red line, which is entirely to the left of the whole of BJ. So this means that there cannot be any common element of AI and BJ. And this is a contradiction with that.
Thank you.
Yeah. Okay, any more questions about this proof? I do not see too many +1s. Can you indicate whether you are happy with that? Okay, any more doubts? Because I see that. No. Okay, let's continue further. Good. So this was a purely combinatorial proof, an existential proof that there is such a family. Of course, we can then ask an algorithmic question. I'm given a family F. How quickly can we compute a Q representative subfamily? And this is an algorithmic question that is highly non-trivial, and there is a wide range of algorithms in the literature that do this task. We will now prove the simplest possible one with highly suboptimal running time. During the tutorials, there will be another one, which will be the one that we will actually use in the sequel. But now I would like to give you a very simple way of computing a representative family that somehow shows what is actually this thing about. So I claim that if I'm given a family F of P subsets of some universe U and a number Q, then I can compute a Q representative family, which I will denote it like that F hat is contained in F and it is Q representative. And it is of best possible size. So F hat is of size at most P plus Q choose P. and the running time will be fpt with respect to the parameters p and q. The running time will be roughly p to the power q, and there will be a cubic dependence on the size of the family. As I said, there are better ways of doing that, but this one will be very simple. Okay, so let's just emulate the proof. So how the proof of the existence of this family looked like. I started with the whole family F, and I was iteratively removing sets that were irrelevant up till the moment where I had an inclusion-wise minimal family that was Q representative. Yeah? So we can emulate this proof if we have an oracle which for a given set, yes, will tell us whether this set is relevant, in the sense whether I can remove it from my family and still maintain the representativeness. Yeah? So what does it mean that it is relevant? It means that there is some possible future B, so some set of Q vertices B that fits, that for which this is the only one that fits. Yes. So this means that A is intersection, A is disjoint with B, so A and B fit. However, B is not fitting to anybody else in my family F. And what does it mean that it is not? It doesn't fit to anybody else. It is not disjoint with anybody else. This means that it intersects everybody else, which means that B, the set B, must be a hitting set for the whole rest of the family. Yes, for all the elements of my family apart from A. So this is the problem that we need to solve if we want to determine whether a set can be removed safely from my family when computing a representative subfamily. And this essentially boils down to a hitting set problem, right? Because what I need to do, I have a universe U with set A excluded, yes? I would like to spend Q vertices in order to hit all the remaining sets, where all the remaining sets are simply the sets apart from the set A, yes, and of course I cannot hit the elements of A. So checking whether set A is relevant boils down to solving this this instance of hitting set, and all these sets here are of size at most p, because we assumed that that F contains only size things of size at most p. And if you now recall, hitting set problem, there was a very simple branching algorithm for this problem. Namely, if I have a set that is not yet hit, I need to branch which of its elements needs to be included in the solution. I have a budget Q for the number of elements in my hitting set, and each time I'm guessing who will hit a certain set, there are p options. So this is a p power q branching. So I have an algorithm that tests whether a set is relevant in this running time. Yeah, p power q times maybe some polynomial factor for some low-level computations times linear in the size of the family. Yeah. And now I need to, at every step, test all the elements of the family whether they're relevant, yes, and exclude one if it is not. And I do it. I remove guys one by one, so this gives me a cubic dependence on the size of the family. Good. So during the tutorials, during the tutorials, you will see another algorithm for computing a Q representative family. It will be of slightly worse size. So instead of size p plus q, choose p. Yes, we will get a size that is roughly 2 to the power p plus q. Yes, times some smaller order factors, but the running time will be better. The running time will be single exponential in p plus q. Yes, times linear in the size of the family. Yeah, so here we trade the size of the representative family for the running time needed to compute it. Good. Yeah, so now we move to applications of whatever we derived for now, but maybe there are some questions at this point.
I have a question.
Yes.
Whose the given complexity time is not FPT when it comes to the size of universe, because size of family F is some n to some power. There's what is the point of using this Q representative family if we need to spend an XP time to construct it?
So what you mean is that you start with a family of all the n power k or n power p paths of length p, and then this would yield an XP algorithm. Do I understand correctly?
Yes, because it's needed to construct the set of much smaller size.
Yeah, this is a very good point, and this will be answered in the remaining part of this page. Namely, as you point out, indeed, if I was doing it very naively, I constructed this whole family, this large family in the beginning, and then tried to shrink it. Of course, in the beginning, I would lose the whole running time on the construction. But the thing is that we will construct this this representative family step by step, always keeping a small representative family. And this will give us a FPT running time, and this will be a trick that we will see in a moment.
Okay, thank you.
Yeah. Okay, any more questions at this point? Okay, so maybe we can just move to this. So the application to the directed K-path problem. So recall we are given a directed graph. We want to check whether it has a simple path on K vertices. So the idea is that we will iterate through all the p's from 1 up to k. I will use q for k minus p, which is the remaining part of the budget for the path. And for every pair of vertices u and v, yes, we have this family of all these possible partial solutions. So all the paths on p vertices between u and v. This is a family that is too large. We cannot store it explicitly. Yes. However, we will always be always computing not this whole family, but we will always find a Q representative subfamily. Yes. So this is the object that we will actually compute. Yes. Which will be a Q representative family of paths of length p between u and v. And by whatever we did before, we know that there is always such a family of size p plus q choose p, where p plus q, recall this is equal to k. We will actually compute using this this approach a slightly larger family. Namely, we will find a family of size roughly 2 to the k plus small o of k. So instead of storing, so the answer to your question is that instead of storing the whole family p uvp, we will store only its representative subfamily. Okay, so let's do it step by step. So for p equal to 1, yeah, so for paths of length 1, I only need to compute families for the start and the begin and the end being the same vertex u. And clearly I have only one such a reasonable path, which is just a path on a single vertex. Yeah, so the beginning of the computation is clear. So imagine what happens if I computed this family for p equal to k. Yeah, so this means that I computed a zero representative family for the family of all the k paths in my graph, of all the k paths between u and v. And if you think about what does it mean zero representativity, it actually means preserving existence of any solution, yeah, preserving non-emptiness, yeah, because like adding an empty set as a possible extension, I need to preserve at least one solution that fits to the empty set extension. Yes. So this family here is non-zero, is non-empty if and only if the whole family of all the k paths between u and v is non-empty. Yes. So in particular, if this is non-empty, yes, then using this process, I will be able to find to get a non-empty representative family of k-paths between u and v, which in particular contains one k-path that I was looking for. Good. So this means that what we need to do, we need to compute, we need to be able to make a step in this induction, in this iteration. Yes. So given the families of those k-paths, of these representative families for length p minus 1, I want to compute the families for length p. So how do I do it? Imagine that I would like to compute exactly this family. So the representative family for paths of length p from u to v. So how do I do it? So first of all, how a path can look like. So a path from u to v, it looks like that. And certainly before v, yes, it goes from some vertex w to v. So what I can do, I can, for every possible vertex w that is from which there is an edge to v, yes, I can take a path from a representative family of paths from u to v, from u to w, yes, and I can just append v. Yes? So in this way, I took a bunch of representative families from u to every possible predecessor w, yes, and I took all of them and I just brute force appended v at the end. Yes. So what I do know is that these guys are of size at most 2 power k plus small o of k. But in this way, this family Q can be too large, yeah, because I just concatenated, in a sense, a bunch of representative families that it may result in the family Q QUVP being slightly too large. But then I have this procedure of computing a representative subfamily. So let's call this procedure trim. So trim, this is a procedure that computes a Q representative subfamily. So family. Yeah. So what I do, I take this slightly too large family Q. Yes. I apply this algorithm that shrinks it to a Q representative subfamily, and this is my next family PUVP. So then the claim about the correctness is the following: that by the induction assumption, I know that these families Q, P, UW, P minus 1, they Q plus 1 represent the families of all the possible partial solutions of length P minus 1. And then because we essentially took all possible brute force extensions by one vertex, you can easily see that these families Q, yes, they Q represent the family of all possible guys, of all possible partial solutions from U to V of length P. Yes, because I took essentially all possible solutions of length P minus 1 up to representation, yes, and extended them in all possible ways to V. And then what we did at the end, we computed a Q representative subfamily P hat. Yes, so here we computed P hat that is Q representative. Yes, and you can easily see that Q representative is transitive. So if P hat Q represents Q, yes, and Q represents P, then this implies that my new solution, my new family Q represents the family of all possible partial solutions of length P. Good. So this is how the single step of computation works. So let's look at the running time of this. So I knew by induction assumption that my family before, yes, is of size at most 2 power k plus small o of k. Yeah, this is because they were representative families for that were computed before. So now if I apply the all possible extensions, so the extension by the vertex V, let's look at this formula here. Yes. This means that I took at worst n different representative families from before, and to each path of this from these families, I added vertex v. Yeah, so this family Q can be of size at most this. Yes, the previous bound times n times the number of possible predecessors. Yes, but now what do? I do at the end I trim this family Q to a representative subfamily. Yes, p hat that I argued will actually represent the family of all possible partial solutions of length p. So what is the running time of this step? Well, the running time is 2 power p plus q plus order of p plus q. Yeah, so let's write it maybe better as 2 to the power k plus small o of k. Yes, times the size of the subfamily on which I apply it. And now the point is that this family is not of size n to the k or n to the p, but it is actually much smaller. It is of size 2 to the power k plus small o of k times n. And tada, we've got running time 4 power k plus small o of k times n. So the point was not to apply the computation of a representative family to the whole family of partial solutions, but to a pre-computed, slightly too large representative family, and use the transitivity of representation. Yeah. So all in all, we again, after this step, we again managed to find a representative family, PUVP hat, yes, which is of small size. So all in all, we have a polynomial number of those families that we need to compute, yeah, because we have for every possible value of p and for every possible value of u and v, we compute such a family, which boils down to running time like that. And everything was deterministic. Good. So the key idea in this proof, and this is an idea that that comes back all the time in representative sets, is that instead of taking one family at the beginning and shrinking it, we are doing it in this sort of a caterpillar way of computation, that we iteratively expand a family and then trim it using computation of representative sets. Expand it, trim it, expand it, trim it. And in this way, we always maintain a small representative set. And therefore, the computations are working in FPT time. Good. So this was the basic application with running time 4 power k plus small o of k. If you apply the currently best algorithm for computing representative sets, you can improve it to, I think, 2.617 power k times polynomial. This is actually 1 plus golden ratio. Power k. You can do it a little bit better than that. I think 2.5 something is the currently best. But this is the best known for deterministic algorithm, like this 2.25 something. So it is a big open problem whether k-path can be deterministically solved in running time 2 power k times a polynomial. And improving a representative sets computation is one way to go in this respect. Good. So this was a basic applications. Are there questions now? Or if you understood this, please put a +1 or a -1 or raise a question if there are any doubts.
One kind of something that I wasn't, maybe I just missed something. When we expanded, do we have to somehow avoid kind of returning to vertices we've already seen, or do we, or does
yes,
that kind
you are completely right. Here I need to have that this assumes that V is not in P. Yes, so I can add the vertex V to a path only if it is not used before.
Great, thank you.
Yeah. Thanks. That was a very good. This was a very good comment. Yes, of course. Here, this is the point where I check disjointness in a sense. Good. So let me now give you another application of the same principle. Application to the problem called directed long cycle. And this is a problem of similar spirit. Again, we have a directed graph D, and we've got some parameter K, which is the length of the cycle I would like to find. And the question is whether the graph has a cycle on at least K vertices. I do not want to have a cycle on exactly K vertices. I would like to ask whether there is a cycle on at least K vertices. And this is a significantly different question, yeah, because now the cycle can be super long actually, and it still yields a yes answer. So in a sense, this is not like you cannot just apply color coding here because you are looking for an object that is possible of unbounded size. And this is why color coding and different techniques of this kind are not that easy to apply here. But representative sets will actually yield a nice algorithm for this problem with running time, I think 16 power K. You can again improve this running time to, I think, 6 power 7.5 power K times n to the small of 1 using better algorithm for computation of
color
repsets.
coding in the way that we are checking all possible Ks up to n.
Well, you could do this, but this would not give you FPT algorithm.
Okay. Yeah, that's true.
Good. So if I'm looking for a cycle on at least K vertices, in particular, in order to certify that the cycle is that long, I could imagine looking at a path on this cycle on K vertices. Yes. So imagine that, for instance, I've got a cycle and sort of an object that certifies that this cycle is long enough is that I can say that, for instance, this cycle contains a path on K vertices from U to V, and this is this path. So let me give you now a very simple n power K algorithm for this problem. So let our object of study be this family of paths. So simply, this is essentially the same family that we have seen before, the family PUVK. This is the family of all the vertex sets of paths that go from U to V and have K vertices. And so paths looking like that. I start at U, I end with V, yes, and I need to go through K different vertices in the middle. So a trivial n power K algorithm would be the following. I just brute force construct all those families, yes, and for each path looking like that, and for each path looking like that, I check whether I can go back from V to U using a path that is disjoint with the path P. Yeah, so I look whether I can go from V to U using a path Q that is disjoint from P, of course, disjoint apart from sharing the endpoints. So a trivial algorithm would be to go through all the possible K paths in my graph. There are n power K of them. And for each of them, check whether there is this back path. And clearly, if I find such a back path, I see a directed cycle of length at least K, as on the picture. And on the other hand, if there is a cycle on at least K vertices in my graph, I can take K consecutive vertices on the cycle, and then there will be a back path that is disjoint from this prefix, yes, which is just the remainder of the cycle. Yeah, so this is trivial n power K algorithm. And now, if you think about representative sets, the natural way of approaching this problem is maybe we do not need to work with the whole family PUVK, yes, which is of size that is not FPT. Maybe we can restrict attention to some smaller subfamily, yes, a representative subfamily, which will retain essentially the same properties. So yeah, so this is indeed true. We can do it like that, and this is encapsulated in the following lemma. So suppose that I have a yes instance. There is a cycle on at least k vertices. And suppose that instead of working on the full family of all possible k paths between u and v, yes, I look at a subfamily that k represents this family. Yeah. So now note that here I've got k and here I've got k. So now k plus k is actually 2k. Yeah. So all in all, I'm looking at sort of a representative for sets of size 2k. Yeah. Then I claim that there exists u and v in my graph and a path that is in my representative subfamily. Yes, in my, not the whole family of all the k paths between u and v, but in this representative subfamily, yes, for which I can find the backpath. Yes, so if I prove this lemma, I actually can improve this algorithm as follows. Instead of looking at the full family PUV, yes, I look at the family PUV k hat. And here, instead of looking through all the k paths from families PUVK, I look at all the k paths P from the representative subfamilies PUVK hat. Yes? And now, if this family will be small, and it will be small, yes, then this yields a much faster algorithm because I have less k paths to look for, to look for. Yes. So I need to prove this, that if I have a yes instance, then actually I can find a witness, a k cycle on these k vertices, already using a witness from my k representative subfamily. Good. So let's go for the proof. So there is some directed cycle of length at least k, right? So let me take the shortest one. Let C be the shortest cycle subject to the condition that it must be of length at least k. Good. So this is the cycle, C. So let me take a prefix, say from the first vertex of the cycle to the k vertex of the cycle. This is a prefix called P of length or on k vertices. Yeah. And I've got the rest of the cycle, let me call it Q. Yeah, so this is how the cycle C looks like. So now if I look at this picture, let me highlight another set of k vertices. Namely, here I've got this prefix of length on k vertices, P. And then let me look at the next k vertices on my path. Yeah. So this is L, this is a prefix of Q. This consists of k vertices. Obviously, it could happen that that actually Q is shorter than K. Yeah, it consists of less than K vertices. In this case, L is just all the remainder. So L is equal to Q. Yeah, so I take the K next vertices or all of them if there are less, fewer than K of them. Yeah. So yeah, here is L. So here are k next vertices on the path Q. So what I know from the representativity, there are k vertices here. Yes, I know that the path P is disjoint with the vertices L, yeah, because well, this was a simple cycle. So this means that in my representative family P hat, I have a witness that is also disjoint with L. So I've got another path. Maybe it looks like that. Let's call it P hat. Yes, that starts at U, that ends at V. It has k vertices as all the paths in P, and is also disjoint with L. Yeah, this follows from representativity. So now there are two cases. Maybe we are super lucky, and actually we have the case that is not the case that I just drew on the picture, namely that this path P hat is actually already disjoint with all of Q. Yeah, it doesn't intersect this remainder of Q after L. Yes, and in this case, it's golden. We are done. Why? Because we just managed to find, yes, that P hat, yes, is a path in my representative subfamily for which there is a backpath that is disjoint. So yeah, then looking at p hat, yes, will actually give us a solution. So in this case, in case number 1, we are done. So imagine now that we have the other case, the case that I actually drew on the picture, yes, where this p hat, it needs to be disjoint with this vertices L at the beginning of Q, but it can, for some stupid reasons, intersect the remainder of Q, and I cannot argue that now Q would be a valid backpath for p hat. But then what? Then let's travel along Q, yes, and let's look at the first vertex W here, yes, the first vertex that is in the intersection of p hat and Q. And now what do we see? Let me just draw it, and I hope that then you will see where this argument is going. Let me go with Q from V up to the first point, and then follow by p hat. What did we get? We got a directed cycle, yes, because here I was traveling until I found the first vertex on p hat. So if I then follow by p hat, I cannot hit this prefix again. Yeah. So we have a directed cycle, and this directed cycle contains the full L, because I could not hit p hat during L, because p hat was supposed to be disjoint with L. So we got a directed cycle on at least k vertices, which is definitely shorter than my original cycle, because I just took a non-trivial prefix of Q, yes, and a non-trivial suffix of p hat. So this is a contradiction with the fact that we chose C to be the shortest cycle of length at least k. Yeah. So in other words, if I start with any cycle, either I can find it a cycle in a representative family, or I can find a smaller, shorter cycle of length at least k. And the representativity here was used to sort of save those first k vertices in order to certify that the new cycle is long enough. Good. Yeah, so we have managed to prove this lemma. Are there any questions about this proof? Maybe you can put a +1 if you're happy with it. Maybe some questions, comments? I do not see too many +1s. Okay, I do not see also too many people in the room, so so I hope that that this is sort of visible for most of you. Yeah, so this means that by the lemma, yes, it suffices to compute a k representative subfamily of the family of all the k paths for every possible choice of u and of u and v. Yeah. Because then instead of going through all the vertices of PUVK, we will go through all the paths of PUVK. We'll go through all the paths of this representative subfamily, and we do the same thing. We iteratively expand and trim. Yes. So again, PUVP is all the UV paths on P vertices. Yes, and we will compute a representative subfamily, which is now 2k minus p representative. Yeah, because at the end of the day, we want to find a k representative family for p equal to k. Yes, and because this +1 always moves from the representativity to the length of the path that we have in our family, I need to start with 2k. Yeah? So again, I start with paths of length 1, for which I just have the whole family being just a single path. Yes? And then I iteratively add one vertex in every possible way, as before, yes. And then I apply this trimming procedure, the procedure that computes a representative subfamily. And for this, I need now to have 2k minus p representativity. Yeah. So now what we have is that p plus q, yeah, so the representativity plus the sizes of the paths that we are interested in are of size are 2k instead of k as before. And therefore, the families that we are working on are of size 2 power 2k plus small o of k. So the running time of each of these steps, of the trimming steps, yes, is 2 power 2k plus small o of k times linear in the size of the family, yes, which is again 2 power 2k times polynomial in n, because this is the number of families that we compute. And this boils down to the 16 power k that I was promising at the beginning. Yeah, so you see here now already that there is an interplay in all those algorithms for computing representative sets between P on one hand, Q on the other hand, and also the size of the family, which also affects the running time in a significant way. And this is why we have so many different algorithms for computing representative sets, because these algorithms work for different regimes depending on which is actually what is large and what is small. Yeah. Good. Are there questions to this application? I don't hear any. I think that for the remaining 20 minutes, I will actually skip application 3. I will ask Wojtek to do it during the exercises. It's actually really simple and really nice. So I think that this might be a good exercise. And I will spend the 20 last minutes of this lecture to tell you something a little bit more about the generalizations of representative sets that are used in parameterized complexity, because the way we have seen representative sets so far is the most like vanilla way of looking at them, but there are multiple other settings and generalizations and extensions that you can think of, and most of them concern looking at representative sets with respect to matroids. So I expect that many of you haven't seen matroids in your life so far. So this is probably maybe the first time when you see them. This is something that looks very scary at the beginning. It's not that scary after a while, but it is good to see it a few times to get accustomed to this language. So imagine that you've got some universe E. I will use E for the denotation of universe because this is the usual letter that is used in the matroid business. And the matroid is essentially a family of subsets of this universe. Yeah, so this calligraphic I is a family of subsets of this universe, and you think of elements of matroid, so sets in a matroid, as sort of independent sets. This will become clear in a moment why independent sets. So you imagine that a matroid is essentially for every subset of the universe, you say whether it's simple or complicated, and simple means independent. And the intuition behind the matroids is that they sort of encode the greedy properties of this family I. And greedy also will become clearer in a moment. So obviously, it's not just any family of subsets of the universe that is a matroid. This family needs to satisfy certain axioms of a matroid, and here are the axioms. So a family of independent sets forms a matroid. It is a valid family of independent sets if the following axioms are satisfied. First of all, there are two very simple axioms. First of all, empty set is independent, and independent sets are closed undertaking subsets. So if I have an independent set A and I've got a subset of A, then B, the subset, is also independent. And the second condition, it's often called the exchange property. There are actually many equivalent conditions to this one. I think that this one is the most commonly known. So condition M3, this is the core of the matroid definition, and it says the following: imagine that you've got two independent sets, A and B, and one is larger than the other. A is larger than B. Then the condition is that I can extend B using an element of A while preserving independence. So there exists an element E in A minus B, such that even if I add E to B, I still get an independence. Right. So let's see one property that maybe clarify this thing. Namely, if I look at maximal, inclusion-wise maximal independences in matroid, then they all have the same size R. Why? Because if I had two that were of not the same size, then one would be larger than the other, and therefore to the smaller one, I would be able to add an element from the larger one, still preserving independence. Yeah. So this means that all of the maximal independences in the matroid are of the same size. And this maximal size, it's called the rank of the matroid. And the maximal independences in a matroid are called bases of the matroid. So you already probably see that we have got independence, we've got a matroid, we've got basis, rank, and there is some fishy notation about the linear algebra here, and this will become clear in a moment. Good. So is there any question about the definition of a matroid? Maybe +1 if you're happy with the definition. Okay. Good. So let's see some examples. I think that you understand this notion once you see how it actually works in examples. So one example we have already sort of seen before, namely this is the uniform matroid. Namely, a uniform matroid of rank R is just all subsets of the universe of size at most R. Yeah, very easy. So E choose at most R. And clearly M1 and M2 are satisfied. Yeah, it can only shrink the size taking a subset. And for the third axiom, the exchange property, well, if A is larger than B, then simply there exists an element of A that I can add to B. Yeah, because I will, if B is smaller than A, then the threshold R is not yet reached, so I can throw in any element. So you see that this is satisfied. Good. So this is a very simple matroid, and the main and actually sort of only important example of a matroid, like let's say globally important, is the linear matroid, the matroid formed by columns of a matrix. Imagine that you've got some field. If you are not happy with finite fields, imagine that you've got fields, say complex numbers or rational numbers. And imagine that your universe is just a bunch of vectors in a linear space, say of dimension D over this field. Yes. So I've got some dimension D, and my universe are just it's just a family of vectors, a lot of them. And my independence property, my matroid, is formed by all subsets of those vectors that are linearly independent. Yeah. So M1 and M2 are very clear. Yeah, empty set is linearly independent, and a subset of a linearly independent set is independent. Yes. So let's check the exchange property, the M3. If I have two independent sets in this in this family, yes. So two sets of vectors that are linearly independent, and one is larger than the other, then this means that well, the first set of vectors, because they are linear independent, it spans some linear subspace. The second one also spans some linear subspace. But because there are more vectors in the first basis than in the second basis, yes, this the dimension of the space spanned by A is strictly larger than the dimension of the space spanned by B. And this means that this space spanned by A must strictly stick out of the space spanned by B. So this means that there is a vector from A that does not belong to the linear span of the vectors from B. What does it mean? This means that I can add this vector to B while preserving linear independence. Yeah, because if this vector is, if here is the space spanned by B and here is this vector E that is not in this, then it is actually linearly independent of whatever is in this subspace. Yeah? So this is this exchange property in linear spaces and with respect to the notion of linear independence. And this exchange property is especially designed to extract a combinatorial core of how bases or sets of linear independent vectors behave in linear spaces. It is the combinatorial principle behind the combinatorics of sets of linear independent vectors. And in essence, matroids are combinatorial objects where the combinatorial structure behind them resembles that of linear spaces, that of vectors in linear spaces with the condition of being linearly independent as the condition for independence in the matroid. Good. So in essence, I said that this is the only reasonable example. This is of course not true, but we were very happy if our matroid that we are working with actually has a structure that can be somehow modeled by vectors in a linear space. So I will say that the matroid is representable over some field F. Yes. If I can find a representation, the representation is just that to every element of my universe, I assign a vector in, say, f to the d for some dimension d, in such a way that the independence is exactly modeled by linear independence of the associated vectors. So a subset of the universe S should be independent in the matroid if and only if in the representation the corresponding vectors are linearly independent. So in a sense, this explains the structure of a matroid through an assignment of vectors in some finite dimensional space. So let's see an example of this. I claim that a uniform matroid of, say, of rank R over a universe of size n is actually representable over any sufficiently large field, over any field of size at least n, more than n. How do I make such a representation? So I've got a universe from 1 up to n, yes, E1 up to En. These are the elements of my universe. And let me take different non-zero elements of the field, yes, lambda 1, lambda n. Yes, and associate E1 with lambda 1, E2 with lambda 2, and so on in the following sense. That my representation looks as follows. If I want to assign a vector to an element EI, the vector that's assigned is this sort of geometric progression vector. 1, lambda I square, and so on, lambda I to the power R minus 1. So this is my representation. This is an assignment that to each element of the ground set assigns some vector from the field power D, power R. So why is this representation faithful? Well, if I have a subset of a universe of size at most R, say of size R, then I claim that the set of corresponding vectors is independent. And why is it? Because if I just put them next to each other, this is this Vandermonde matrix, yes, where you have the geometric progressions in every column and geometric progression with different multipliers. Yeah? And then you know from linear algebra, if you have the Vandermonde matrix with different geometric sequences in every column, then this matrix is non-singular, and you actually have a closed formula for its determinant. And obviously, if I took a set of size more than R, of size larger than R, then I am working with in a space that is R-dimensional. I cannot have more than R linear independent vectors in such a space. So here, a set S corresponds to a linear independent set of vectors if and only if the set is of size at most R, and this is exactly what we needed to prove for the faithfulness of the representation. Any questions to this example? Maybe some +1s if you are not yet lost. I see a +½ What is the remaining half? Okay, maybe the next example, the next bunch of examples will clarify this. So I wanted to give you a bunch of matroids that are related to the combinatorial setting of graphs, and these are matroids that can be explicitly used in parameterized complexity in connection to representative sets, as will be clear by a result that I will state at the end. So first example is the graphic matroid. So imagine you've got a graph, and the universe of our matroid will be all the edges of my graph, and I will say that the set of edges is independent if it is acyclic. So this would be an independent set in my matroid, because I do not see any cycle in this among the red edges. But if I, for instance, add this edge here, I would suddenly see a cycle, and then this set would be dependent. Yes. So I just defined a universe and a family of sets, and then you would need to actually prove that this is indeed a valid matroid. So I will not prove it directly combinatorially. I will prove it by giving a representation of this matroid. A representation over any field. So a representation will take any edge of my graph, yes, and associate with it a vector in f power v, where essentially these are vectors over the field f that are indexed by the vertices of the graph. Yeah? So, and the representation would be very simple. If I have an edge uv, I associate a vector consisting of all the zeros, apart from putting a 1 at vertex u and a -1 at vertex v. Yeah. And I claim that this is actually a representation of this matroid, in the sense that a set of edges is acyclic if and only if the corresponding vectors, the vector that I associate with those edges, is linearly independent. So let me prove only one implication, namely, if there is a cycle, then it is dependent. And this is given on this picture. So imagine you've got a cycle among the red edges. So how this cycle looks like in this matrix formed by putting those columns corresponding, putting those vectors corresponding to those edges next to each other. Where for the first edge, I've got 1 and -1. Yes, so say that this is this edge. Yes. Then for the next edge, say this edge, I've got here a 1 and a -1. Yes. And maybe it is a reverse, but I can always flip it. It doesn't matter. Yes. The next one is again a 1 and -1. 1 and a -1. And then I've got a cyclic here, a cycle here. So I've got a 1 and -1 from the beginning. Yeah. So I've got the corresponding matrix consisting of those vectors has this minor. Yeah? And you see that having this structure yes, gives you that this set of vectors is actually dependent. Why? Because if I add all of them, I get a zero vector. And you would need to prove the other implication, namely that if I've got an acyclic set of edges, yes, then this corresponds to a non-singular matrix. And this you can easily prove by performing sort of Gaussian elimination from the leaves of this forest upwards. This is quite easy to see. Good. So this was a graphic matroid. This was a graphic matroid. There's also a co-graphic matroid. This is a matroid consisting of all the subsets of edges, such that if I remove this subset of edges, the graph stays connected. Turns out this is also a matroid. It satisfies the exchange property. Maybe Wojtek will do this as part of the tutorials. And this is also representable over any field. Then finally, I wanted to give you two examples of really important matroids that are quite non-trivial that they are matroids, namely a transversal matroid. Imagine you've got a bipartite graph with bipartition A and B, yes, and the element of the ground set of the transversal matroid is one of the sides, say A, and a set is independent. Here, a set X is independent if I can match it to the other side, if I can find a matching to the other side. And then again, subset of a vertex subset that can be saturated can be clearly saturated, and you can prove also an exchange property here that you've got this extension property using augmenting paths in here. So this is also a transversal matroid, and also it is representable over sufficiently large fields. And finally, if we have matchings, it is not very far from matchings to flows. And the last example is the Gammoid. And Gammoid is the following matroid. You've got a directed graph, two sets of vertices S and T, and you look at all the subsets of S. So subsets of S will be independent. So the universe is S, the sources. And the subset X of the sources is independent if you can find a flow from X to T. So in a sense, this is a very similar example to the transversal matroid. It's like a generalization of transversal matroid. Yeah, and the transversal matroid, A would be S, B would be T, and this path would be just single edges. And it turns out that this is also a matroid, and the proof actually uses the fact that transversal matroid is a matroid. And once you think about it, matchings in bipartite graphs, flows, spanning trees, the graphic matroid, these are all combinatorial objects for which you've got non-trivial polynomial time algorithm using greedy principles, right? For instance, if you know the max weight spanning tree algorithm, the Prim or Kruskal algorithm, or Borówka algorithm, all of them are based on a greedy principle of putting more and more edges into the spanning tree. Similarly, computing a matching in a bipartite graph, it can be seen as a greedy procedure of putting more and more edges into the matching and finding the next ones using augmenting paths. And similarly, the proof of Menger's theorem about flows and cuts, it is also essentially a greedy procedure. And all of those procedures can be explained by the fact that the underlying combinatorial structure is matroid. And all of those procedures can be understood as a single generic procedure that is called the maximum weight problem on a matroid. Good, but this is not the moment where I go into the theory of matroids because it's essentially a topic for another semester course. I wanted to say finally a few words about applications of matroids to representative sets. So imagine that again I've got some family of P subsets, of a universe U, maybe universe E. And I've got also some matroid structure on this universe. Yes. And now I would like to extend the notion of representability of representative sets or representative families to representative families with respect to this matroid structure. So the definition is exactly the same, apart from one aspect, namely, if I've got some subfamily f hat, then it Q represents my family f with respect to this matroid structure if for every possible future B, so a set of Q vertices, if there is somebody from my original family that fits, then there is also somebody from my trimmed representative family that fits. But now I redefine the notion of fitting. Instead of saying fits means disjoint, I say fits means disjoint, and they together give me an independent set in the matroid. So in a sense, I not only now require that elements should be disjoint, I require that the elements should be disjoint, and together they have some additional combinatorial property that is governed by a matroid structure. Yeah. So for instance, in the set of, if we are working in a graphic matroid, I could imagine that I've got P, a subset of P edges, a subset of Q edges, and together they must be disjoint, and in combination there must be a cyclic. And this would be governed by a graphic matroid I here. And the thing is that if you've got a matroid together with a representation over some field, then all of the properties of representative sets that I told you about, they work the same way. You can also find a Q representative subfamily, also of size P plus Q choose P. So you do not lose anything on the bound from the Bollobas Lemma. Yes? And given the representation, you can find this subfamily in this running time. Linear in the size of the family on which we are working, times some factors depending on P and Q in a parametric way. And by time, I mean the number of operations on the field F, in the field F. So in many more complicated applications of representative sets in parameterized complexity, you are not working on a representative set with just disjointness property, which essentially boils down to working on a uniform matroid, but you are working on the representative sets where you additionally have some matroid that guards the notion of fitting for representative sets. And the fact that many of the matroids that we work with have efficiently computable representations give us quite a lot of power in many problems. And I hope that Wojtek will cover one or two applications of some of the matroids that I showed to you during the tutorials in parameterized complexity, and in particular this theorem. You can actually see the proof of this theorem in the Platypus book. It is not hard. It's a bit of juggling with linear algebra. Good. Are there questions about matroids and about whatever I told now? This is the end of the lecture. Questions, problems, doubts? If not, then thanks again for the lecture. I apologize again for being again slightly late.